we just saw that example of a doubled sequence which had different limits depending on the order of the limiting operation, and so kind of said that we have to be careful in exchanging the sum and the limit, and so let's try to sweep that issue kind of away on this side of the board. So there's a lot of tools to handle this, and probably the more common one in this situation would be called dominated convergence, and you're welcome to kind of look up what that is. That's a very common tool in probability theory. Now I'm going to show you something a little bit more, maybe a bit more classic and something interesting. So see, this is a paper on kind of talks about this specific problem. This is, I think, from 1912 or 1913. You can look up the year. I'll post it on Gaucho Space. But essentially, right on the first page, right out the bat, it kind of tells you sort of when you can and when you cannot. Right, it gives you the necessary and sufficient conditions when the L there is a limit, right, and when the limit of the sum is equal to the sum of the limit. And so, what's the condition? And this is, you can find this in pretty much any real analysis book, and that's this concept of uniform convergence, right? So a uniformly convergent series in this case, and in the case of, a sequence, a double index sequence, then it's just going to be a uniform convergence of that particular sequence. And so let's see what it looks like in our case. Right, so essentially translating what I just showed you over to our setting, you'd see that our sum converges uniformly, which was the condition for putting the limit in, if this residual goes to 0 in absolute value. So this residual is kind of the remainder of the sum that I had in the previous clip, right? So those xi's are all the enumeration of the entire state space S. And you can see that the sum here is not from 1 to n like I had before, but now it's the residual, the remaining part, n plus 1 all the way to infinity. And as long as this residual goes to 0, and this right here is why this is the name uniform convergence comes from the insertion of this, what's called the supremum operator. You can think of it as just a maximum. And so the idea is that if the maximum of this residual converges to 0, then the sequence is uniformly convergent, and in that case you're justified in exchanging the limit and the sum. And so the only kind of thing that's remaining for us to do is to justify this residual condition from essentially coming from that paper from the year 1912, right? So you can kind of see that there's interest in these things about 100 years ago when a lot of these kind of tools were being developed. Okay, so how do we bound this above? Well, I mean, that should be easy. I know that each probability is bounded above by 1, and so my claim is going to be that this is just the sum from I equals n plus 1 to infinity pi xi, right? And all I've done here, the absolute values, first of all, they don't matter because everything is positive. And all I've done is I've taken each one of those probabilities right there and bounded them above by 1, which has to be true of any probability, right? And so, hopefully you kind of see how this came to be, right? Again, no absolute values because everything is positive, or rather non-negative. And now the question is, would this, I can replace this or bound this above by this sum here, and then take the limit, and then, hopefully you're convinced as to why this should go to 0, right? If the sum over all the xi's here goes to 1, then clearly if I take the index up, I'm reducing that sum, taking it over less and less things, and so the limit will indeed go to 0, right? So this part is true because the sum over all x of pi x is equal to 1, right? And so if I take less and less terms, right, eventually when the limit goes, right, when that limit removes all the elements of my sum, the residual will go to 0, and that's one way to justify this type of operation. Right? Another one again is the dominated convergence theorem, and you can also compare all this with Ross now, and he does something a little bit different. I think you'll find that it's a bit more difficult to justify the exchange of the limit and the sum in his case, but I haven't taken a look carefully, so I don't know, maybe you can, so take a look at that if you're interested. Okay, so now we're back to the first step of the proof of the lemma in the last clip, and that has to do with the statement up above, right? So the one that starts with pi y, and it's asking you to prove that statement for all k, right? And so again, anytime someone asks you to prove something for all integers, you better start thinking induction, or you should probably start thinking induction. And so that's the statement we're trying to prove. We're going to try to go with induction on k. The base case is 0, and hopefully, well, in fact, the base case could be made anything. So why don't we make it 1? So, in fact, I would encourage you to try base case equals 0 as well. Both, k equals 0 and k equals 1 would work, and they would work for different reasons, and both are interesting. For k equals 1, it's a bit easier, and the reason is that this would follow from the global balance equations. Right, so global balance gives you this identity right away when k equals 1, and so you can start with that off as your base case, and then it's a nice exercise to try k equals 0, because what is pxy when k is equal to 0, when you have 0 steps? Well, it's going to be an indicator function. It's going to be 1 and x when x is equal to y, and 0 otherwise. Right, so that sum, which is in fact, I should write as over x. So if you actually go through that sum, all the elements except for the yth one will get knocked out, and you'll also arrive at a true statement. Right, so it's literally true for all k greater or equal to 0, but in this case we are actually working the proof from 1. Right, doesn't matter. Right? But 0 also works, right? So it's a fun exercise to work that through. Next step in induction is to assume the statement is true for k minus 1, and then we're going to show it for k. Right. So now, one thing that comes up a lot, I see people struggling with, is sort of not knowing, always reading the statement from left to right when trying to verify it. You don't necessarily, if you're trying to verify an equality, you don't necessarily need to start on the left, right? And so here it actually pays to start on the right, and so as long as we get from one to the other, we're okay. So we are again assuming that this is true for k minus 1, and now we have to prove it true for k. So essentially we're proving this statement, and I'm going to start on this side and hopefully end up here. And if I can end up here, right, induction takes over and you establish it for all integers. Okay. So we start on the right side, and the first thing to do is to apply Chapman-Kolmogorov, right? So that is what I've done here. So this part right here is Chapman-Kolmogorov. Okay, and you can see how that is, right? So trip of length k split into k minus 1 and one step to reach the final point. The next part is, let's see, what did I do here? I pulled out a PZY and switched the sums, right? So now the sums are switched. This is a little bit delicate as well, so I think it's okay for this class to kind of just write it, but if you want to know when to interchange sums, when they're finite, it's always okay. When you have an infinite state space, right, in this class we're maybe taking things up a level, a little bit of complexity, right, and so we can have infinite state spaces, and in that case good thing to remember is that you can exchange two infinite sums when the things you're summing are all non-negative. And so it's a nice trick. It's called the Fubini-Tonelli theorem, sometimes just the Tonelli theorem. So feel free to look that up if you're interested. But again, when you have two infinite sums and the things you're summing are all non-negative, you feel free to kind of exchange things around. What's next? So I pulled out the zy out of this sum because it doesn't depend on x, and I landed on this. And now the question is, what is that? Well, this part, by the inductive hypothesis, is equal to, right? So this whole part right here, by the inductive hypothesis, is equal to pi z. So hopefully you see why that is. Right, I have a k minus 1, and it's the same statement up there, except that instead of a y, I have a z, so that's pi z, right? So this is inductive hypothesis on using z instead of y, so I can erase this and put a pi z. And then finally, and hopefully you see that this is nothing else but pi y, and this part is true by global balance, right? If you change these, right, you'd have exactly how, what the global balance equations are, right? It doesn't matter what the order of multiplication there is. That's just global balance. And so, I guess what else is there to say here? Yeah, we did it. That wraps up the proof, right? So by assuming k minus 1, we clearly applied the inductive hypothesis in the previous step, and we just showed that that leads to it being true for k, and therefore by induction, right, it's true for any k. So yeah, wraps up the proof of the previous lemma, and in the next clip we'll try to kind of put a few more of these things together.